is what IB expects you to know about circular motion. This is from your IB syllabus, 2.4 basically, variety of things to know about circular motion, and this is what we will hopefully cover today. So this was my original target, but this is what we need to talk about. You just swing this stopper around to try to hit the target. One of the things I want you to realize is that when you're swinging the stopper around, it's going in a circle. When you let go of the string, what does it do? It goes in a straight line. Once you've released the force making it go in a circle, it goes in a straight line. It does not do this. It does not do this. Okay? It's Newton's first law. When you let go of the string, there's no more force acting on it, and so it continues on in a straight line. So in order to hit the target, okay, and you're swinging it horizontally, when do you let it go? When is it moving towards the target? When it's beside you, okay? When it's beside you. What direction is it moving when it's in front of you? Yeah, to the side, right? So if you let it go when it's in front of you, it's going to go flying sideways. So the trick is you got to let it go when it's over here, because that's when it's going that way. So, okay, this is the top-down view of what we just did. Okay. It doesn't matter what is under. Like, it would still do the same thing no matter what view it is. Okay. Unless there's gravity involved, right? So then the question is, now let's look at this. If I have an object moving with a constant velocity and I exert a force, or I cause it to accelerate at a right angle to the direction it's traveling, what is the result of that action? Okay, so here's my object moving with a nice constant velocity, and I exert a force causing it to accelerate perpendicular to the direction it's traveling. Will that cause the object to speed up or just slow down? Speed up, slow down? Totally a trick question. Because look, notice my force is not in the direction it's moving. It's perpendicular to the direction it's moving. It will neither speed up or slow down, but what will it do? Change direction. Okay, this will cause it to change direction. And if I have it now moving this way, and I continue to exert a force perpendicular to the direction it's moving, what's it going to do? It's going to keep changing direction. Okay? And I continue to exert a force perpendicular to it. If I do that the whole time, my object will start to go in a circle, as long as I'm constantly pulling it inward. Okay?
So you're also changing the force.
Changing the direction of the force. The force is always perpendicular to the direction of motion. This is how we create uniform circular motion. Okay? So when I apply a force perpendicular to the direction of travel, I still have a constant speed. The speed does not change. It doesn't speed up or slow down, but what I do get is a new direction. And this is how we generate uniform circular motion. Okay? So yes, because it's changing its velocity, not its speed. Uniform circular motion. So this is what we're talking about. What do we mean when we say uniform circular motion? What is it that is uniform? What is it that remains constant? What do you think, Luke?
The speed.
The speed is one thing. And what else? You could think of it that way, but we can debate that a little bit.
Oh, it's the force going in, right? This force changes, but the speed stays.
The speed is constant. The size of the circle is also constant. If those two things are constant, if we have something moving around a constant radius at a constant speed, we say that it's doing uniform circular motion, and we can then do some stuff with it, okay? In our previous drawing, our previous analysis, what direction was I exerting a force in order to make uniform circular motion happen? What direction is the force? What? Towards the center. That is also the direction that the acceleration will be, and there's a word for that in physics. It's called centripetal. Centripetal means center-seeking. So when I have a centripetal force or a centripetal acceleration, I will get uniform circular motion when the force is always exerted towards the center of the circle. When we're swinging this rubber stopper, it's the string that's exerting a force towards the center of the circle, and that's what makes the stopper go around. If the string gets cut, this thing will fly off in a straight line, okay? Except for gravity will pull it down. The velocity of the object at any given instant is a tangent to the circle. Okay, it's perpendicular to the force, perpendicular to the acceleration. It's tangential to the circle, and a tangent being a straight line that touches the circle just at that one location. That's how I can figure out what direction the velocity is. So let's look at that visually, what we're talking about here. There we go. So something is moving in uniform circular motion. It's moving around with a constant speed, but its velocity is not constant. Why is the velocity not constant? Because it's changing direction. It has a constant speed with a constantly changing direction. The acceleration will always be towards the center of the circle, and the velocity will be perpendicular to that force, that acceleration. So the velocity is tangential to the circle. A tangent is just a straight line that touches the circle at that point, and that is the direction of the velocity. Tangential to the circle, perpendicular to the force of the acceleration. There's a better picture of it. Okay? So what direction is the velocity right there of the object? Point with your fingers, the direction of the velocity. Okay? The velocity is here. Okay? What direction is the force? Okay? Force is centripetal, centripetal. So we can do this anywhere. What direction is the velocity there? Down, you guys are good. And the force, centripetal. Okay? Easy stuff right there. Circular motion, easy stuff. Let's look at this real quick. If I have an object going around in circular motion, at point A, its velocity is to the right. And at point B, sometime later, its velocity is kind of down and to the right. Way back when, we talked about change in velocity over change in time. What was change in velocity over change in time? Acceleration. So if I want to find the acceleration of this object, I need to figure out how its velocity has changed. And how do we find a change in anything? Subtraction. And what do you subtract? What from what? You subtract the initial from the final. Okay, wherever you end up, you subtract where you started. That will give you the change. So really, if I want to find the change in velocity, I need to go v2 minus v1, which is this, right? And if you remember with vectors, when I subtract vectors, basically I flip the second one and add them. So the subtraction is the same thing as this, plus v1. Okay, and when adding vectors, I just draw them tip to tail. And lo and behold, my change in velocity is that, which you can see that right there. The reason this is interesting is because that is, your change in velocity is the direction of the acceleration. So from here to here, it's showing us that the acceleration is centripetal when I look at how my velocity has changed. Okay? There is some math we can do with all this, and there are some equations that will help us deal with this. So let's see if we can figure out those equations to figure out how fast something is accelerating and how much force it needs. Yes, it is. So there's the equation for finding the acceleration of an object that is undergoing uniform circular motion. If I know its speed and I know the radius of the circle, I can find its acceleration by squaring the speed and dividing it by the radius of the circle. That's your first equation for circular motion. The second equation is very similar. Let me show you where the second equation comes from, even though, okay, centripetal. When I'm going in a circle, well, hold on a second, let's back up for a second. What was our original definition of velocity? Distance times time? Or divided by time? Distance divided by time, right? Okay. So, when I'm going in circular motion, if I've gone around once, what distance have I traveled? That's your displacement is none, but what's your distance? Relative to a circle, what do we call that? Close.
Circumference. Pi times diameter.
Circumference. So going around once, it's 2 pi r, or pi times the diameter. That's the circumference of the circle. The time it takes to go around a circle once has a very special name, and it's called, we give it a capital T, and it's called period. The period is the time it takes an object to go around a circle once, okay? This word and this idea of the period is going to come back a lot when we study waves. So for circular motion, I can take distance, the circumference, divided by the period, and that will give me the velocity of the object. If I take this equation and plug it in over here for v, I will get this equation. That's where the second one comes from, okay? That's not in your data booklet. It's not a bad thing to be able to use sometimes. Sure. Distance divided by time. Okay. Centripetal. Okay. So if I have an object that is doing uniform circular motion, I now have two equations that allow me to calculate its acceleration. The first one, oh, you guys figure it out. It's all right. Haven't gotten to the third. If you know the velocity or the speed of the object and the radius of the circle, you can calculate its acceleration. Or if you know the radius of the circle and the period or the time it takes to go around once, you can also calculate its acceleration. So those two equations are in your data booklet. Hang on one second, Carson. The third equation is this one, which is basically Newton's second law. If you want to figure out how much force it takes to make something go in a circle, or even around a part of a circle, around a corner, this is called centripetal force. And in order to do that, you just take the mass of the object times either of these acceleration equations, okay? So what it would look like once you've done it is you can go m 4 pi squared r over t squared. That's the centripetal force. Or mv squared over r. Either way. It's just the mass times either of those two equations. That'll tell you how much force is needed to make something go around. What are some examples of types of things that exert centripetal forces? Give me some examples of some centripetal forces in the universe. Okay, cars going around a corner. What exerts the centripetal force when a car goes around a corner? The wheels. Can you be more specific? Can you be more specific? And what do you mean by traction? Friction. Friction between the tire and the road is what exerts the centripetal force on a car. If there's no friction, there's no turning. You will not turn. Okay? Just doesn't happen. Yeah. No friction. Exactly.
How about tension, like on the string?
Uh-huh. Okay. Oh, I hate it when that happens. So remember that to do circular motion, you don't necessarily have to do a complete circle. Here's a turn in a road. Many of you can drive. For many of us older people, that's a scary concept. But, you know, okay, this is like the turn on Owl Creek Road. And remember that centripetal force equals mv squared over r. What this equation tells us is that I can calculate how much force is needed to go around this corner. What are the three things that determine how much force is needed? Mass, velocity, and radius. Ideally, there's only so much force that I'm going to have because there's only so much friction between the tires and the road. You with me? I've got a maximum force. So what I want to do is I want to minimize how much force is needed for me to make this turn. And what can I do to minimize how much force is needed? I can get a bigger radius, or less mass, or slow down. And of those three variables, which one will have the greatest effect? Why slowing down, Carson? Because it's squared.
So for each part you get smaller,
it actually has a greatest effect of anything. Cutting your speed in half does 4 times the effect, whereas cutting your radius in half, or doubling your radius, only cuts the force in half. So what that means is you guys all should slow down. You drive way too fast, okay? Slow down. Well, then can you hang on to it? Okay. Okay, so let's look at what this looks like for us. Arg. When you're going around a corner, first things first, slow down before you get to the corner. That's the most important thing. You got to slow down. Slowing down helps. 2, you can make the radius bigger or make the mass lighter. So 1, throw your sister out or your brother, right? That helps. 2, make the radius bigger. Now, I don't suggest this, but if you've ever watched a car race, you might have noticed that they go from here to here to here when they go around a corner. That's a big radius turn. They try to make the radius as big as possible so they can carry as much speed and not go sliding out. What you don't want to do is this. Whoa, whoa, okay. Bad way to go around the corner. That's a real small radius turn. That requires a lot of force. I don't recommend doing the race car thing because obviously we live in a world where there's traffic, okay, and so that can be dangerous. But if you have a closed track and you can go as wide as you want, that's a great thing to do. You might also notice that sometimes this is just like the turn right down here by the football field. You notice that? And there's a guardrail over here. And this guardrail is very dented. It has lots of smashes into it because oftentimes there's ice right here. And imagine this for a second. You're driving around this corner, you've got good friction, things are good, and you hit a patch of ice which has a lower coefficient of friction. No more centripetal force, your car goes straight into the side, okay? And that's what happens. So slow down before you go around the corner. Okay. So if we had time, we would do this practice problem, but we don't have time. So try it at some point if you want. Okay, it's a good one. And oh, here's another one. We'd try this one too, but you know we don't have time. So, but just looking at it real quick, what would you do? What equation would you use here?
I got it.
What do you think?
So you don't have velocity. You would use the second equation, right?
Use the second equation. And what would t be? But of course you'd want to turn that into seconds, right? Right. Okay. And you'd want the r to be in meters. What's that?
You do it and then you convert it out to a second.
I wouldn't.
Okay.
Okay. Okay, Ferris wheel. Now, here's a situation where you're spinning something not horizontally, but you're spinning it vertically. And this gets a little bit trickier, but it's really not that bad. At which point, intuitively, at point A or point B, will there be the greatest tension in the string? Point B, you would say, right? I mean, it makes sense. It's going to be pulling harder at B. We can actually calculate how hard it's pulling, because if I know, please stop that soon. If I know how fast it's moving and I know the radius of the circle, I can calculate the centripetal force needed to make this thing go in a circle, right? Up here, the centripetal force is equal to the tension plus gravity, right? Because they're going the same direction. Down here, the centripetal force is equal to the tension minus gravity, because they're going in opposite directions. If I rearrange this, I'll notice that the tension in the string is the centripetal force minus gravity. And down here, the tension in the string is the centripetal force plus gravity. So there's more tension down here. Because I'm adding the weight here, whereas up there I'm subtracting the weight. Okay. Vertically, right, exactly. That's a vertical circle, okay? Finally, here's another problem. Try it out sometime if you want. Okay, great. There we go. Okay, you're going around a corner. People always talk about, okay, like a car's going around a corner. I feel myself being pulled outward. That's called a centrifugal force, okay? Centrifugal means center-fearing. Centripetal means center-seeking, okay? So this would be what's called a centrifugal force. It does not exist. It is non-existent, okay? People talk about it all the time. And you can have a centrifugal force. And an example would be if there was like a monkey on a bicycle, okay, riding around the corner outside of me who grabbed me by the head and pulled me out. That would be a centrifugal force, the monkey pulling me out. But when I'm driving my car around the corner, there's usually not a monkey. There's usually nothing pulling me out, okay? So why do you feel like you're moving out? Well, because of inertia. You want to go straight. Your car is turning. You feel like you're being pulled out, but you're really not. You're really going straight, and the car's not going straight. It's actually kind of it's a weird thing. There is no force acting centrifugally. There is a force acting centripetally. Yes. You aren't at first until you either hit the wall of the car and then you start going around the corner, or you fall out the door and then you keep going straight.
But you can have like a centrifuge, like they do that, like